In question 12 part A, we're given f of x equals this function, ax is less than 1, a cannot equal to 0, and we're asked to prove by induction that the nth derivative of f of x is given by this horrible formula. So, as I always start my induction proofs, proof by PMI, principle of mathematical induction. So, P1, I have to show that the LHS equals RHS. So, the base case, the first derivative of f of x is this, second derivative of f of x give me this. So, I can say that LHS equals RHS. So, P1 is true. Now, I'll rub this out. Assume true for n equals k, and I've written here that P1 is true. So this implies that the kth derivative of f is equal to a to the k times 2k minus 1 factorial times, what was it? It was 1 minus ax to the minus 2k plus 1 over 2 all over 2 to the 2k minus 1 multiplied by k minus 1 factorial. Now we want to show this. So as the usual step 2 is we consider k plus 1. So left hand side we're going to have f of k plus 1 of x, and right hand side we're going to have a to the k plus 1 times 2 times k, no, I'll just, so 2 times k plus 1 is 2k plus 2 minus 1, so 2k plus 1 factorial times 1 minus ax to the 2k minus 2k plus 3 over 2, is that right? Yes. Over 2 to the 2 times 2 to the 2k plus 1, and then k plus 1 minus 1 is simply k factorial. So we want to show that the left hand side, the k plus 1 derivative is equal to this. So that's the same thing as saying f prime of f of k of x, f of k of x, which is equal to f prime of f, the k derivative we said is this, so I can substitute that in, a to the k times 2k minus 1 factorial, 1 minus ax to the minus 2k plus 1 over 2 all over 2 to the 2k minus 1 times k minus 1 factorial. So we want the derivative of this, and we notice that since we're getting the derivative in terms of x, these are all in terms of k, so they can just be seen as constants. This is the only thing that's actually in terms of x, so I can write this outside of the derivative, so I'll just write that on its own. So I have a to the k multiplied by 2k minus 1 factorial over 2 to the 2k minus 1 times k minus 1 factorial multiplied by the derivative of this. Now, the way I found the derivative earlier was that I have to find, basically using the chain rule, it would be the derivative of whatever's inside of this function. So derivative of 1 is 0, derivative of minus ax is minus a, so minus a, and then it's like normal power rule, this goes down to that, times minus 2k plus 1 over 2 times 1 minus ax, 1 minus ax to the minus 2k plus 1 over 2 minus 2 over 2 is the same thing as saying minus 2k plus 1 over 2. I'm just writing that. And we have minus 2k minus 1 minus 2, which is minus 2k minus 3 all over 2, which is minus 2k plus 3. With the brackets, obviously. Minus 2k plus 3 all over 2. And now what I can do is this minus and this minus are going to cancel out. I'm dividing by 2 here, so I can take that 2 over here and make it 2 to the 2k minus 1 times 2, so it'll be 2 to the 2k. And this a and this a is going to make a to the k plus 1. So that is equal to a to the k plus 1 times 2k minus 1 factorial times 2k plus 1 multiplied by 1 minus ax to the minus 2k plus 3 over 2 all over 2 to the 2k minus 1 times 2 is 2 to the 2k times k minus 1 factorial. And observing the right hand side, so observing what we want it to become, 2 to the 2k we want is 2 to the 2k plus 1, and we want this k minus 1 factorial is just k factorial. But we also want 2k plus 1 factorial. And over here we have 2k plus 1 times 2k minus 1 factorial. So if we can somehow make this into a factorial and improve that, we're sorted. So in order to do that, we notice that 2k plus 1 factorial is simply 2k plus 1 times 2k times 2k minus 1 factorial. So if I can somehow have a 2k here, I get 2k plus 1 factorial. So if I multiply this top side by 2k, bottom side by 2k, I can hopefully get somewhere. So I write a to the k plus 1. Now multiplying by 2k, dividing by 2k, I will get 2k plus 1 factorial times 1 minus ax to the minus 2k plus 3 over 2 all over. Now we'll have 2 to the 2k times 2k times k minus 1 factorial. And now 2 to the 2k times 2k is again 2 to the 2k times 2 times k minus 1 factorial. 2 to the 2k times 2 is 2 to the 2k plus 1. So that's equal to a to the k plus 1. So I'm just rewriting the top half. 2k plus 1 factorial, 1 minus ax to the minus 2k plus 3 over 2, all over 2 to the 2k plus 1. And then we have k times k minus 1 factorial, which is simply k factorial. And this is our right-hand side. So we have proven the statement by mathematical induction. So I can say that P1 is true and Pk plus 1 is true whenever Pk is true. Therefore, Pn is true for all n is in the positive integers. Amazing. In part C, we're asked to show that 1 minus 2x to the minus a half times 1 minus 4x to the minus a half is approximately equal to this. From earlier, we're given that f of x, where f of x is this, is approximately equal to this Maclaurin expansion up to the x squared term. So if I simply substitute a equals 2 into this, I'll get this expansion. Substitute a equals 4, I'll get this expansion. So I'll do that. So sub a equals 2, that's approximately 1 plus x plus 3 over 8 times 4, 12 over 8, which is 3 over 2 x squared. Sub a equals to 4, that's approximately 1 plus 2x plus 3 over 8 times 16, which is 48 over 8, which is 6x squared. 6x squared. So now I have to show that this times this is approximately equal to this. So I'll say that 1 plus x plus 3 over 2 x squared times 1 plus 2x plus 6x squared. Multiplying by 1, I'm going to get this. So if I multiply this by 1, this by 1, this by 1, I'll get 1 plus x plus 3 over 2x squared again. If I multiply this by 1, I get 2x plus 2x squared. If I add my 2x squares, then I can simply see that I won't get something close to 19. So I can add another term. Since this is all approximate, I don't know how many terms I have to add. If I do 2x times this, that's an x cubed term, which won't be there. So I'll add this x squared term plus 6x squared. That's equal to, there's only 1, so 1 plus 3x plus 2x squared plus 8x squared plus 3 over 2x squared is 3 over 2 plus 16 over 2, 19 over 2, 19 over 2x squared. And that can be written as 2 plus 6x plus 19 all over 2, 19x squared all over 2, which is what we want. So, as required. And that's our solution to part C. In part D, we're given that in order for f of x, being this function, to converge, we have a restriction that the modulus of ax, or the absolute value, must be less than 1. And it asks what restriction on x must be placed in order for our functions to hold true. So in order to do that, we have been given two restrictions. We've been using a equals 2 and a equals 4. So for a equals 2, we get that the modulus of 2x must be less than 1. A equals 4, modulus of 4x must be less than 1. So you can say that modulus x must be less than a half, since you can take out a constant, that's a rule. And modulus of x, I can derive that later if you'd like, must be less than a fourth. Now, the question is, which one of these are we actually going to end up using? This is the same thing as saying a half is less than x is less than a half, minus a half, sorry. This is a fourth is less than x is less than a fourth. A fourth is clearly bigger than, sorry, a half is bigger than a fourth. So this restriction is smaller, has a smaller domain than this restriction, which means that this can be rejected. So this is the solution. In part E, we're asked to use x equals 1 over 10 to give us an approximate value for the square root of 3. So in order to do that, I think we just substitute x equals 1 over 10 into all of this. So that's going to be very tedious, but anything for the marks. 2 times 1 over 10 to the minus a half, 1 minus 4 times 1 over 10 to the minus a half equals, it's approximately equal to 2 plus 6 times 1 over 10 plus 19 times 1 over 10 all over 2. 1 minus 2 over 10 is 1 minus 1 over 5, which is 3 over 5. So 1 minus 2 over 10, 1 minus 1 over 5. No, which is 4 over 5, yeah. 4 over 5. Wait, I just want to make sure I've said that correctly. 1 minus 1 over 5, 5 over 5 minus, yeah, okay, that's right. Multiplied by 1 minus 2 over 5, which is 3 over 5 to the minus a half. So approximately 2 plus 6 over 10 plus 19 over...
The recording seems to have cut off here, but basically what I'd done is, since I had some number multiplied by root 3 on the left hand side, and then on the right hand side I had again my terms, I made root 3 the subject, and that gave me an approximate value for root 3, and the answer, the solution that I had at the end was root 3 is approximately equal to 500 over 279.